Hello folks, today I want us to learn a bit about processors, the CPU, the brains of a computer. Now on the right hand side of your screen you should be able to see an Intel CPU. There are a few CPU makers in the world, Intel and AMD are the two big ones, but Intel are currently the biggest. Now this processor is about 2 square centimeters of silicon, and in it contains a lot of transistors, and it uses these transistors to perform simple computing calculations, which you're going to try in a few minutes. But it can do a lot of these every single second. And want to have a guess at how many it can do? You're probably way off. Put it this way, I will take the answer to the nearest million. The answer, the number of calculations per second it can do is, drum roll please, that sounds weird on my table, 3.1 billion calculations per second. But if you want to know something even more scary than that, every 18 months the number of process transistors inside a processor will double. That's right, doubles. It's done so every 18 months for 40 years, and looks like that's going to continue. So in 2020 there will be approximately 6.2 billion transistors inside a CPU. That's kind of scary, but also kind of cool because it can do some very cool things. Now, with these videos, guys, at the start I'm going to tell you 3 questions which by the end of the video I hope you'll be able to tell me the answer to. So, by the end of the video you'll be able to describe to me 2 different CPU architectures. You'll be able to describe to me the stages of a fetch, decode, execute cycle, and you'll know at least 3 ways to speed up your CPU. You might want to write these down now, guys. Just pause the video, write these down, so then if you hear something you write it down and say, oh yes, and then at the end you can answer these questions with ease. So, now you've done that. Now, this is a picture which is quite important to computer scientists. Now there are 3 things here which you might be interested in. Firstly is the man in the centre, Julian Oppenheimer. Mr. Oppenheimer was a professor of mathematics in the US who led the Manhattan Project during World War II and built the world's first ever atomic bomb. Clever man, I think you'd agree. Behind him, that big machine behind him, is a 1940s computer. And that 1940s computer is about as powerful today as your calculator is. Probably slightly less actually. You'll see there's no screen on it, no keyboard, no mouse, nothing. Oh boy, apologies to the helicopter. I live right next door to an RAF base, so one of them is doing some practice at the moment. But I'll keep going, I'm determined to do this. So, you have got the computer from the 1940s. You have got Julian Oppenheimer standing right here, and next to him is a chap who we are especially interested in. His name is Jan von Neumann. Jan von Neumann was a Hungarian and what is known as a polymath. Polymaths are effectively geniuses, and he was a genius in mathematics. People have sometimes described him as one of the world's last great mathematical thinkers. This man was designing artificial intelligence programs in the 1930s, before computers even existed, which is kind of scary. However, not only did he work with Oppenheimer on the atomic bomb project, but he also designed the first processors, and his designs are still in use today. Every PC or Mac you buy today will use his design of CPU, which is pretty cool, I think. So, this was his design. His design was relatively simple, but that's why it took off. Firstly, you have input devices here, like say a keyboard or a mouse or a tapper of some sort, and an output device, maybe a typewriter or a printer or a screen, a monitor. And then inside you had a processing unit with a control and ALU unit inside, you'll learn about these later, and a memory unit in the same system. A very simple design, and this is one reason why it took off so quickly. The alternative was this, the Harvard model. The Harvard professors preferred to have every single unit separately attached to each other, so they could upgrade one at a time. They also had instruction memory and data memory. So any data had to go in data memory, and any instructions or programs had to go in instruction memory, and you couldn't put them anywhere else, which started to get very, very complicated. So people didn't use it. Chip makers went with the von Neumann architecture. So we said a few minutes ago that this chip had got or could produce 3.1 billion calculations a second. Now you might be thinking, 3.1 billion what? What are these calculations you're going on about? Well, the computer has 3 different types of calculations which it does inside the CPU, and these are as follows. CPU. Now, here we have got a fetch, decode, execute cycle. The computer will do these 3.1 billion times a second. Fetch, decode, execute. The fetch one here, fetch, the computer will go to the computer memory, the RAM. There is fetch, there is decode, and there is execute. The fetch stage, which I'm going to put my laser pointer on here so you can see, is when the computer will go to the memory and fetch an instruction, a part of the program, the thing the computer has to do next. Then the computer will take the fetched piece of information and it will decode it. It will have a look and say, okay, what are you? Where are you going? Good. And it will send it to the right place. When it's in the right place, in the right format, this instruction, the computer will send it to be executed and the computer will run it. And then, when that's done, the whole charade starts again. You will then have a nice, simple system. Fetch, decode, execute. Get that from memory, get it ready for the CPU, process it, get more information from memory, and so on and so forth. This is how this works. Now a computer can do 3.1 billion of these instructions a second. So say that's 1 billion fetches, 1 billion decodes, and 1 billion executes. But there are faster ways of doing this, and they can be achieved using something called streamlining. Streamlining will look a bit like this. Over here, we have got F for fetch, D for decode, and E for execute. And here I've got 1, 2, 3, 4, 5. Imagine those to be microseconds. So every microsecond you can fetch, decode, or execute. So A, my first instruction, so that's an instruction to go to my CPU. A is fetched in microsecond 1, it is decoded in microsecond 2, and it's executed in microsecond 3. Nice and easy, you think. But some folks started getting a bit clever with this. They thought, okay, so in the second microsecond, about here, A is being decoded, but nothing is being fetched. So they said, why don't you fetch the next instruction, which is B. So while A is decoded, B is fetched. And then, while A is executed, they said, okay, well, B can be decoded. But wait, nothing's being fetched. So they started to fetch the C. And then the next time round, while B is being executed, C can be decoded and D can be fetched. And you see the idea. So doing it like this, the CPU can process 3 times the amount of data it otherwise could. So instead of processing 1 billion instructions a second, the CPU can process 3.1 billion instructions a second, which is a massive boost, I'm sure you'd agree. So, now, when you buy a CPU, you will see that there are various things you can do to speed it up. I have taken an advert here from AMD. They are quite a big chip maker. The AMD Ryzen. That's a good name. I like that name. A Ryzen CPU. Now there are a few things here in these nice instructions, which I'm going to use my laser pointer on here, which you can look at and you can ways of speeding up your CPU. Firstly, there's cores or threads. Cores are, until about 10 years ago, you bought one CPU, you had one core, one brain in the center doing all the work. Now, in the last 10 years or so, chip makers have started to add 2, 4, 8, 16 cores onto a CPU. So the CPU won't go any faster, but it will be able to do twice as much or 16 times as much work in the same time. Which, to me, that's pretty cool. Then, you've also got the clock speed. So base clock and max boost clock. So the base clock is 3.6 gigahertz, and the max boost clock is 4.2. Now, max boost clocks normally come from overclocking. The CPU, the silicon here, is designed to run at 3.6 gigahertz a second. But they're actually saying here, some people who want the fastest speeds, the best performance on their chips, they will make them so they run faster, they will supply more power, they will hack the motherboards, and they will make them run much, much, much faster. The problem with doing this, though, is that CPUs produce a lot of heat, and I mean a lot of heat. The chip makers, AMD and Intel, tend to go looking at NASA for people who are used to dealing with heat from re-entering the atmosphere, to recruit to help them design fans and reduce the heat going through their CPUs. So, if you are going to overclock your CPU, you have to make very, very sure that you have got a cool enough chip. Otherwise it will die and you'll never be able to use it again. So the last thing here I want to show you about is cache memory. Now, we've talked about the computer going to the memory to get instructions. Fair enough. This CPU has got 19 megabytes of cache memory. Now, a new computer today could have 8 or 16 gigabytes of RAM, but having a cache RAM of 19 megabytes, you're like, that's a bit small. What's the point in that? Well, the reason for it is any instructions you are using a lot can be copied into here to the cache RAM, the cache memory, and then used there. And because it's on the CPU, it is so much faster. So it's useful for storing things you always use. Okay, so to improve your CPU speed, try and increase the number of cores the system has. Get the fastest clock you can or overclock it. But if you overclock, be sure your cooling systems are the best you can find. And cache RAM, the more cache, the faster your CPU will be. Okay? Now, last but not least, we have got integrated systems. Say you look in your car, when you get into a car, and often now they have small computer screens telling you how fast you're going, how much fuel you've got, what's the route you're going, what radio station you're playing, what videos you playing if you're in a very nice car, which is handy. That's a computer, isn't it? It runs using a CPU and it will process itself very quickly. But it's not like a computer because you can't do tasks on it, you can't load software on it, you can't try and transfer things to other computers. It's designed only to work in that system. And that makes it, guys, an integrated system. Okay? If you look at washing machines, if your parents buy a washing machine, you will see on the top a little display screen with lots of different signals and information. Again, this will give you, this runs off a microchip, like the one I have in the picture here, but all the information will only be used by that machine. You can't transfer it to, say, an iron or a cooker or a fridge or to an MP3 player. Nope, it won't work. It only works in that environment, in that system. So guys, that is how integrated systems work. So, last but not least, I'll go through these, pausing to give you a chance to get your answer written down, and then I will tell you what the answer should be. So, you'll be able to describe two CPU architectures. So pause now, and then I'll go through it. Okay guys, so CPU architectures. The two ones we have learnt today are the Harvard and von Neumann. Von Neumann's architecture is a simple architecture where you have got the arithmetic logic unit and the control unit inside the chip, and that is directly linked to a general purpose memory that can process any instructions it wants or data it needs to. Harvard architecture, on the other hand, likes to keep things separate and has memory for instructions or data, just to complicate life. The stage is the fetch, decode, execute cycle. Well, fetch is where you get information from the memory and transfer it to be decoded. The CPU will make sure it's in the right format and put it in the right place to be executed. And then finally, the execution stage will come, the CPU will run the code, and then it will start the whole process over and over again. And then we had 3 ways to speed up your CPU. Well, one of them is to use streamlining on your fetch, decode, execute cycle, which we talked about earlier. But the 3 specific ways were: 1, get a CPU with more cores. So the more cores, the quicker your programs will load, hopefully. Secondly, get the fastest clock speed you can. And that will do it. You can even overclock it as well, but you have to be careful of heat if you're going to do that, as they do a habit of burning out the chips. And finally, you have got the cache RAM. The more cache RAM you have, the more information your CPU can store on the CPU in quick, easy to access places. So, if you've learnt about all those 3 in this lesson, fantastic. Keep going for the workbook, and I will see you next time. Adios.